Hi, I'm Jeff Mucklin, and this is Science at Home, which is brought to you by the Nurture Nature Center. In previous episodes, we have explored all kinds of objects within our solar system, such as the Sun or the planets that orbit our Sun, but we will now travel to solar systems far, far away as we learn about exoplanets. Like the planets of our own solar system, exoplanets are objects that are too small to be considered a star, and they're too big to be considered an asteroid or a comet like the one seen here. The only difference is that they orbit a star other than ours. The other stars in the galaxy are indeed very far, far away, and for hundreds of years, natural philosophers and scientists could only speculate on the possible existence of planets orbiting the other stars in the universe. It was incredibly difficult to detect planets beyond our solar system until quite recently. Telescopes, for example, were not powerful enough to directly image the planets orbiting even the closest stars. If I point my camera at a very bright source of light in a dark space, it becomes very difficult to tell if there are any objects near that light back there in the darkness. And that's because the camera can't see both the bright source of light and any dimmer objects near it. We have a similar problem when we point our telescopes at distant stars. They are 1,000,000 or 1,000,000,000 times brighter than any planets that might be orbiting them, because planets don't emit their own light. They can only reflect the light from the star they're orbiting around. So the glare from the starlight makes it impossible to see the planet. But what we do have are coronagraphs. These are small black disks that we can put in front of our telescope, and if the coronagraph is just the right size, it will block only the starlight, and any light that is coming from objects near the star can still reach our telescope. So here I've got my makeshift coronagraph, and I'm now blocking the light, and you should see a small object right next to it. So there you go. We have detected an exoplanet. So detecting exoplanets using even the best telescopes we have in space with coronagraphs is just really difficult to observe them directly. Though sometimes gravitational lensing events can occur that can make it much easier to see an exoplanet. This occurs because massive objects bend space, just as this heavy ball here is distorting and bending this fabric sheet. Massive objects in space, like stars, bend space around them. Now, if there is a star system very far away from us, but between our telescope and that distant star system there's another massive star, light might bend around that closer star and allow us to see very clearly another star system on the other side of it. Gravity can act as a lens and make it easier for us to detect what would otherwise be impossible to see. Gravity helps us in other ways because most of the exoplanets that have ever been found have not been found through direct observation. They've been found through indirect methods. Remember, it's just really hard to see exoplanets, but what we can see very clearly are the stars themselves. And there are ways that we can figure out if there is an exoplanet orbiting around a star by paying very careful attention to, say, the way that star moves. So as a planet orbits, or an exoplanet orbits around a star, the planet moves in a very wide circle around the star, but the star also moves slightly. It's pulled slightly towards the exoplanet orbiting around it. And if we watch distant star systems very carefully, we should be able to see a very characteristic wobble if there's an exoplanet orbiting around them. It's much easier to detect the wobble of a star not by actually seeing them moving back and forth, but by measuring the frequency of light emitted by these stars. Because as stars move towards and away from us, the frequency of light that they emit shifts. It shifts due to the Doppler Effect. Now, most people are more familiar with the Doppler Effect in terms of sound. We know that a sound, say like this, that's a 1,000 hertz sound, that same sound source will sound very different if it's moving towards us. The sound waves will be compressed and it will be a higher frequency sound. It will sound like a higher frequency sound to us. And if the same sound source is moving away from us, it will sound like a lower frequency sound. because the waves will be spread out as the sound source moves away from us. Now, although it is harder to detect the Doppler shift for light, it works on the same principle. If we have, say, an object that is emitting white light that is moving towards us, that white light the light waves will be compressed and it will appear bluer. And if that same white light is moving away from us, the light waves will be spread out a little bit and it will appear slightly redder to us. And the faster the object is moving, the more apparent this Doppler shift is. We can't see it because objects have to be moving at extremely high speeds, considerable fractions of the speed of light, before we would actually notice the blue and red shift. But we have very sensitive equipment that can detect even very tiny shifts. By far the most effective method so far for finding exoplanets has been the transit method. This is another indirect method where we're not actually directly seeing the exoplanets, but some way that they're changing the star that we can see. We see transits within our own solar system, by the way. This data set here shows you a transit that occurred in 2012 when Venus, right there it goes right now, appeared to pass in front of the sun from our perspective here on the Earth. If an exoplanet passes between that distant star and our telescope, we will see a brief dip in the brightness of that star. Now, I've set up an experiment here that shows the same effect. I have my spotlight again, and it's creating a terrible glare, and you can't see that there is a ball just like this one that's on a stick, and I'm going to use a radio-controlled car to move that ball in front of the light, and you should notice a slight dip in the brightness of that light. And between the transit method and the Doppler shift method and directly observing exoplanets, we've actually now have a list of almost 5,000 exoplanets that we've discovered. For most of these exoplanets, we know very little about what they're actually like. We know roughly how big they are, and we can figure out, how long their orbital period is. So we can use that information to take some educated guesses about what conditions might be like. So artists, with their talents, have produced images of what these exoplanets might be like, and I can show you them on the Science on a Sphere. This exoplanet is Kepler 10b. It orbits very close to the star that it orbits around, and it could be tidally locked, which means that one side of it always faces towards that star. And because it's so close, that side's going to be incredibly hot, incredibly sunbaked. This is exoplanet TRAPPIST-1H. TRAPPIST-1H is closer to the star that it orbits than Mercury is to our own sun. But that star that it orbits around is much smaller, much dimmer, and cooler than our own sun. So even though it's very close to it, it's probably very cold on TRAPPIST-1H. This unusual looking exoplanet is TRAPPIST-1D. It's in the same system as the previous exoplanet we looked at, but it's even closer to that star. And so you'd expect that it might be really hot, but that star is very, very cool. It's an ultra-cool dwarf star. It's probably actually only slightly warmer than it is here on the Earth. And who knows, this could be a planet that has life. I hope you were inspired by those exoplanets, because for this video's at-home activity, we're going to be making our very own exoplanet art. Now, there will be more details in the link provided, but for this activity, you're going to need some flat river rocks. You're also going to need some acrylic paint of various colors, and you're going to need something to stir that paint together a little. As you choose colors to mix together to make your exoplanet, perhaps consider what kind of exoplanet, a tidally locked planet that's roasted on one side, like that exoplanet we saw earlier. Or maybe you're trying to make an alien Earth-like world, a world with blues and greens and browns here. Right now is an incredibly exciting time to be interested in exoplanets. NASA very soon will be deploying the James Webb Space Telescope. This is a model of the James Webb Space Telescope. It is an orbiting telescope. It is so sensitive that it will allow us to actually learn what the atmospheres of some of these exoplanets are actually like. I hope you've enjoyed learning about exoplanets with me today, and I hope to see you next time.